E-rate and the digital education explosion are creating increased broadband network demands. Scalable wide area networks, or WANs, are an integral part of meeting those demands. How these WANs are designed will have a direct effect on their potential to grow and scale. It's important for districts to look at the most common architectures and determine best practices for their district's growth over the next 7 to 10 years and plan accordingly. One common architecture design is the hub-and-spoke architecture. Let's take a look at this architecture. Each circuit originates at a centralized hub or data center that terminates at each remote campus location. This could also be described as multiple single point-to-point circuits, all originating at the same point or location. Hub-and-spoke solutions can offer a cheap and easy alternative for districts due to the ease of management and simplicity of design. The design also isolates each school on its own and can be seen as secure. Additionally, if a data center moves, this may or may not void all of the pairs, as those pairs may belong within a larger sheath that could be tapped at a new location without a full rebuild. However, there are also some disadvantages of hub-and-spoke topology. For example, if that data center should move outside the current fiber footprint, you will need to redirect the fiber from the schools to the new data center, which could result in considerable time and cost. If the district has a second data center with links from each remote site, this does offer an additional level of protection against a single point of failure. However, districts planning for a 7 to 10-year network need to consider that data centers may change locations based on availability, price, or space. Such a move would have far-reaching impacts for a hub-and-spoke design. There are distance limitations on networks as they grow as well. 10 gigs will reach up to 80 kilometers. However, 40 gigs will be limited to 25 to 40 kilometers, and 100 gigs will be limited to 10 kilometers. And much more powerful core equipment is required to run these high-bandwidth networks. Next, let's look at ring topology. In this topology, each end or core node is connected physically to 2 or more other nodes, including the data center, using different fibers on diversely routed paths, creating a ring. This topology's reliability is advantageous because if one node fails, or if at any point the fiber is broken or compromised, the network hardware can reroute the data around the failure point, typically in less than 50 microseconds. Through best practices, a district would create a core ring made up of geographically diverse core sites. This architecture allows for growth on the network should more core sites need to be added anywhere on the network, as well as provide closer aggregation points for remote sites, thereby reducing the cost of client optics. Now let's consider the disadvantages of a ring network. One disadvantage could be the initial cost of building the network. This increased cost is related to the core equipment or fiber construction, which can be higher than simple point-to-point networks. These costs are most often offset by the lower total cost of ownership and the ability for the network to be elastic versus a rigid hub-and-spoke design. Another possible disadvantage in a ring architecture is in upgrading capacity. All nodes may need to be upgraded, and adding and removing nodes may impact adjacent nodes. Service providers build their networks based on best practices such as ring topologies to create the maximum resiliency, high availability, and the ability to scale. They have been building this way for customers since the early 1990s. If a district currently has a lit carrier service from any service provider host, there's a better than 95% chance those services are built on a ring architecture. However, the lit service provided to their customer may be seen as a logical hub-and-spoke, cloud, or ring topology. When creating their own networks through dark fiber or self-construction, districts should consider the physical architecture of the network and its resiliency and focus on reducing points of failure where possible. Districts are now service providers to their schools and should consider a mix of these technologies. Ultimately, the right option for districts should be based on cost, needs of a school, and expected future geographic reach of the district. A hybrid solution is created with a number of core hub sites, with the objective of having a limited number of remote, as to not overextend the network sites. 5 to 10 sites are typically best practice. The various hubs on the ring can then act as the center of the multiple point-to-point connections, terminating at various remote points. These individual remote point-to-point terminations have a higher probability of failure than rings, so it is recommended they be locations that are non-critical and can accept occasional outages. Alternatively, these remote sites could have a second path to the separate core site on the network, providing an additional level of protection. The district's main goal in deciding on a network architect should not initially be based on cost alone, as some network designs will have lower upfront costs, but are much more expensive as the networks scale. The best practices around service provider networks demonstrate the path districts should follow to provide the most scalable, cost-effective, and efficient networks for their students and teachers. Take a look at the next video on Category 1 options.